talking about chapter 5 here. We started talking about nomenclature last time. I know you guys then went to lab and he did some nomenclature talk with you, I think. Yes. If not, we're just going to make sure everybody's on the same page, I guess. So we've been talking about ionic compounds here and nomenclature. And when we deal with ionic compounds, it is always the metal and non-metal combination that we got going on. And whenever you have a metal and non-metal, we always are going to get that transfer of electrons from the metal to the non-metal. The result of that is, again, we'll get our cation that's positively charged and our anion that is negatively charged. And it is always the metal that is the most important one to look at when you are doing nomenclature. So pretty much whenever a metal is involved, that is really what you should look at. There's really sort of two types of ionic compounds that we sometimes name. They're sometimes referred to as type 1 and type 2 ionic compounds. And really, there is no difference in terms of what makes up those ionic compounds. They're both metals and non-metals, but the difference is really the metal and sort of where the metal falls. So in a type 1 compound, the metal and non-metal here, our metal is from usually group 1, 2, 3 are its zinc, cadmium, or silver. And really, again, what all these guys have in common is it is a fixed positive charge. So this is a fixed positive charge. And whenever we see that sort of metal involved, we pretty much don't have to worry about too much other than following the way that we name it, which is the whole name of the metal and our non-metal here will get the IDE part at the end of it. Yes. So if we look at it of that, we have something like say CaBr2. We have something like K2O, and say something like, thank you, LiH, for example. And let's say we have some of these, we'll do some names here just to make sure. Let's do like magnesium chloride. Let's do aluminum oxide and silver nitride. All right, so why don't you take a couple minutes here just to make sure everybody's on the same page for these type 1 compounds. Give the names on the left there, the proper formulas there on the right. And just to be clear, in lab, you went over, right? Type 1 and type 2? Okay, just want to make sure. Okay, let's take a look, see how we're doing. So again, you always just want to analyze what you're dealing with. So calcium is a metal, bromine is a non-metal. Once again, whenever the metal is involved, that is the most important one. So that is calcium, which means it has a fixed charge. And that's pretty much all you need for the name. You're just going to call it calcium, whole name of the metal. The non-metal will get the IDE. And as we might have talked about before, has no effect to there. So again, no prefixes or anything like that in that case. Any question on that one there? Looking at the next one, once again, that is potassium, which is a metal, oxygen, which is a non-metal. So once again, here it is the metal, which is group 1, which again means it's a type 1 and a fixed charge. So again, that's all we need. And we'll go whole name here of the metal, potassium. And our oxygen gets the oxide at the end, IDE. Just like the 2 on the bromine, the 2 here has no effect on the name either when we're dealing with metal and non-metal. Lastly, here we have lithium, which is a metal. We have hydrogen, which is a non-metal. And in this case, lithium is still group 1, which means it would be lithium. And this would be hydride, IDE. This is actually lithium with a +1 charge, and our hydrogen, the negative version of hydrogen in this case, that has a -1 charge. Remember, hydrogen, again, is the only one that can kind of go both ways there, plus or minus, and it's typically minus when it comes after a metal, like in this situation here. Any question on any of those names there? Coming to the other side, we want to just kind of put it together. Metal in group 2, which means it has a +2 charge, which is group 7, has a -1 charge. And again, when we put it together, we want to get to 0. So we really need an extra chloride there. And that means that our formula would be MgCl2 in this case. Looking at the next one, which is aluminum oxide. Aluminum is group 3, so it has a fixed +3 charge. Oxide is oxygen, which has a -2 charge because it is group 6. Common number actually is 6 between those two. So really you need a couple of these aluminums to get to +6. And you need 3 of these oxygens to get to -6. So if we just write what we got there, that's 2 aluminums and 3 oxides there. Gets us there to Al2O3. Any question on those two? We have silver here, which is a metal. It's a transition metal, but it's one of those transition metals that have a fixed positive charge. So that is silver with a +1 charge. Nitride is nitrogen, which is group 5 on the periodic table, has a -3 charge. So once again here, when we put them together, we actually need more of the silver. If it helped you could draw it out, and you need 3 of them. So that would give you 3 silvers and 1 nitrogen. Any question on any of these type 1 guys here? So in addition to type 1, you also talked about type 2 ionic compounds. And once again, type 2 ionic compounds are pretty much the same deal. The only difference is here our metal, which is the most important thing, has a variable positive charge. And these are typically our transition metals, obviously, except for our zinc and cadmium and silver are just to the right, where you have things like lead and tin on the periodic table below the staircase. Those also have a variable charge. Because they can have a variable charge, we do need to use Roman numerals here, and this is where we use Roman numerals. Once again, we use the whole name of the metal. Our non-metal, once again, will replace the ending there with the IDE. And in the middle here, we use Roman numerals. A reminder that the Roman numerals are not how many metals you have or the overall charge. It is just the positive charge on one individual metal that you would have. So it is just the positive charge on one of the metals. So if we had obviously FeCl3, in this particular case, iron is a metal, Cl is a non-metal. Iron is a transition metal, dead center there on the periodic table, which means it's a type 2. So who knows what the charge is? The good news is always with type 2 guys, you'll know what the charge is. So Cl is group 7, which means it has a -1 charge. And frankly, there are 3 of them. Gives you a -3 overall charge. So to balance it out to 0 there, our iron 3 charge in this case. And that just gets incorporated into the name. And this would be iron Roman numeral 3. And once again, the multiple chlorides have no effect on the name. And again, it is the Roman numeral is the charge, not how many you have. So that would be iron Roman numeral 3. The reason obviously we need to do that is if we come across something like FeCl2, in this particular case, our iron would not be +3 because we have one less. It would actually be +2 in this case, and that would be iron Roman numeral 2 chloride. So again, for the charge that is on it. So because essentially these guys could have variable types of charges, we do need to include the Roman numeral in our naming to let people know, in this case, this is the guy with the +2 charge, and the other case is the guy with the +3 charge. The reason obviously we don't need to do that with any type of type 1 compound is because those guys have fixed charges, which means no matter what happens, sodium is always going to be +1. It will never be anything other than that. So you don't need to tell people that it's going to be +1. Any questions on that there? So we'll do a few here just to make sure. Let's do PbO2. Let's do Cu2O. And let's do Fe2O3. And then let's do nickel 4 chloride. And let's do chromium 2 phosphide. All right, so proper name on the left there and formula on the right. Okay, let's take a look at these here. So starting the first one here, we have Pb, which is lead, which is a metal. We have oxygen, which is a non-metal. So automatically that tells us it is a ionic compound for sure. We want to look at the metal, which is lead, which actually doesn't fall in the transition metal region, but it is just to the right there underneath the staircase. So those guys also have multiple types of charges like tin, which is Sn, bismuth, those guys, antimony, which is Sb. Follow type 2 naming with these guys, which means we do want to kind of figure out what our charges there on the lead. We know for sure we have 2 of the oxides, which are group 6, which means overall that is a -4 negative charge happening, which means in this case it is +4 for the lead here, not 2. And this would be lead Roman numeral 4 because of the charge. And again, this would be oxide. So this is a good example of, again, sometimes people are taught just to kind of switch the charges and stuff like that. And this is a case where it would not work correctly if you just blindly do it. So as we might have talked about earlier, you could just blindly put in, 90-ish or so % of the time, you'll be good. But there definitely are a lot of cases where you'll get the wrong formula and stuff like that. Any questions on there? Coming here, this is copper, which is a metal. We got oxygen, which is a non-metal. So once again, it is ionic. Our copper is dead center there in the transition metal region. So that definitely tells us it can have multiple types of charges. We actually have 2 coppers in this case. Each of them needs to be a charge. We have only 1 oxygen here, which is -2. That means in this particular case, each of the copper has to carry a +1 charge to get us the overall +2 charge. And this would then be copper Roman numeral 1 oxide. So once again, the Roman numeral goes for the charge, not how many you got going on there. And that should be copper Roman numeral 1 oxide. Question on that one there. Coming down here, that's our good friend iron. That's our old friend oxygen. Apparently I went with O. I'm very popular here today. Iron, again, being the transition metal, we're going to figure it out. In this case, we actually have 2 of the iron. We have 3 of the oxygen. And again, if you just want to draw it out and add it up, that is a -6, which means each of the iron in this case actually needs to be +3 to balance it out. And that would mean that this guy here would be iron Roman numeral 3. And once again, it would be oxide here since I didn't pick any different negative guy on these examples, apparently. Any question on any of those 3? a Roman numeral it for how many metals there are or overall charge, but it is just if you took one of the positive metals out, what the individual positive charge is on it. Any questions on any of those there? Now, if we have the name and we're rolling backwards, when we see the Roman numeral, the nice thing about that is it tells us exactly what the charge is on the nickel. So the nickel has a +4 charge because of that. Chloride is group 7, which means it has a -1 charge. So in this case, we actually need more of the chlorides. We need 4 of them to balance it out. So that would give us NiCl4 in this case here, which would be nickel Roman numeral 4 chloride. Same thing here with the Roman numeral there. That tells us that the chromium actually is carrying a +2 charge. And phosphide is phosphorus on the periodic table, which is a -3 because it's group 5. And that means common number there is going to be 6 to put that together correctly. So to get our chromium to 6, we actually need a grand total of 3 of them. And to get our phosphide to 6, we need 2 of them. So that's going to give us Cr3P2 in this case. Any questions on those? So really important to always, obviously, as we talked about, ionic compounds, anytime anything that's positive, negative coming together needs to equal 0, and the simplest way to do so. And again, the Roman numeral needed for any metal that has more than one charge, which is essentially your transition metals, and just to the right there underneath the staircase. Any questions on type 2, guys? Okay, I just want to make sure we're all on the same page in terms of all that there. You might also talk about that in terms of type 2. There are sort of an older way of naming, which we will not use in here, but you can use ferrous or ferric, for example. So these are some examples we did, which is here. So sort of an older way of naming where that doesn't use Roman numerals is to use ic or us, and it does use sort of the old sort of school name for these guys. So ferric or ferrous for iron, cupric or cuprous for copper. Usually the ic is the larger positive charge when you see that. And the us is the lower positive charge. So for example, ferric would be the +3 version of iron, and ferrous would be the +2 version. Cupric would be the +2 version for copper. Cuprous would be the +1 version. So here's a table I think you have in your book. We really won't use these. They do use sort of older names. If you get to 1B, you'll see these kind of names come back again when you talk about some other type of naming. But for the most part in here, for sure, you should use Roman numerals for these type 2 sort of guys as you go through it. One you should watch out is also confuses people is mercury. So that is mercury, and that is mercury. And again, oddly, the one with all the 2s is mercury 1. And the one with only 1 2 is mercury 2. And that's because mercury 1 comes as a dimer of 2 mercury 1s together. So you get 2. So the way you kind of know it is mercury 2 is that 2 sort of hangs out. So for example, HgO versus Hg2O. And this is mercury 2 oxide. This guy where the extra 2 is on the bottom is actually mercury 1 oxide. So that extra 2 sort of stays with the formula. You only need one of those because this guy technically is Hg2 plus 2 and O2 minus. So that extra 2 sort of finds its way into the formula a lot of times with mercury 1. And that's sort of how you can kind of distinguish, kind of mercury 1 from mercury 2 a lot of times. Because they both will end up obviously with the same overall charge of +2, but that extra 2 on the bottom gets you to the mercury 1 that's happening. Any questions on that there? All right, so that should catch us up here. All right, so we talked about that. We did those. We did some examples. We'll roll through here. All right. All right, so then let's get to sort of the next type of naming. And this is sort of a decision tree between type 1 and type 2. And again, it is really based off of that metal. Let's then talk about type 3 compounds. Type 3 compounds are molecular compounds, and they are are covalent compounds. So these are covalent, are molecular. And these are basically two nonmetals together. So much like what we talked about with bonding, with these type of guys, we are going to have sharing of electrons, which means there really is no charges you have to worry about. There's no balancing charges. Frankly, they are the easiest ones to do. And they are also the ones that people screw up the most on because they try to do all kinds of weird things and stuff like that. So they are very easy to do. Don't have to worry about charges. Just really got to count what is there. And this is really where we use prefixes. So people always want to use prefixes everywhere else but here. This is actually the right place to use prefixes, where we use something like mono for 1, di for 2, tri for 3. And there's a table, I think, coming up here that has all this on it. Tetra, that's 4. Penta is 5. Hexa is 6. Hepta is 7. Octa is 8. Nona, why not, is 9. And deca, deca is 10. So these are prefixes where we use them. There are a couple of things in terms of the prefix that we do need to take into account. The first one, and really the major one, is we do not use mono on the first name, but it's okay to use it on the second name. So mono is never used for the first name, but you can use it for the second name. So when we get something like CO, for example, here, when we see carbon is a nonmetal, oxygen is a nonmetal, that is a type 3 compound. So really the prefix here would be mono, since there's just one, and the mono for this guy as well. So because we don't use mono on the first name, we basically just use the whole name of the element, which would be carbon. And normally we would use the prefix and the whole name of the first element. The second element gets the IDE treatment at the end, just like all the other kind of second guys gets the IDE. The prefix here would be then mono oxide. Now, this also brings us up to the second sort of thing that sort of occurs when we use prefixes. And when we use prefixes, sometimes we get a couple of vowels that sort of back up to each other, like an O and an O, or an A and an O. And typically speaking, we get rid of the O off of the prefix. So really, this is what is known as carbon monoxide, not carbon monoxide. Yeah, so we do drop that first O off of the prefix. So really the ones where, you know, you run into that is where you back up a prefix vowel of an A and an O, or like an O and an O. So those vowels off of the prefix are typically sort of removed when we do the name. Couple of I's is actually okay. So if you got two I's that back up, you can leave the I's okay. But an A and an O and an O and an O, you typically get rid of that vowel part of the name. So as I mentioned, they only contain nonmetals. And here's basically the rule. And again, I'm not sure if that's the right table anymore, but basically we prefix the first name and we use the whole name of the element, obviously if it needs a prefix. And then we basically prefix the second element, and that gets our normal sort of non-metal with the IDE ending. So first guy, whole name with the prefix, as long as it's not mono. Second guy gets the appropriate prefix and the IDE treatment at the end. You don't have to balance anything, figure out charges. You frankly just need to count and pick the right number prefix to use there. And here's a table again of our prefixes with our awkward sort of names. Sometimes occurs. So again, in each of these sort of prefixes here, we get rid of the A and we get rid of the O. There are, again, a few things that should still go by the common name. So as we talked about before, water should be H2O, not dihydrogen monoxide. Nobody wants to drink of that. And ammonia, which is NH3, has no charge and should not be confused with a polyatomic ion, which is NH4 plus, and ammonium should go by ammonia. CH4, which is the simplest organic guy, and that is methane. So CH4 here. So CH4 is methane, water, and ammonia should always go by sort of their names. In addition, I think we might have talked about it, but just to make sure as well, hydrogen really doesn't follow type 3 sort of naming. So if you have something like HCl, for example, it's really thought of more as an ion and like a type 1 compound, even though it really is a nonmetal. So this is really thought of as like H plus and Cl minus. So this would be hydrogen chloride. And, even if you had two of the hydrogens, something like that, this would be hydrogen sulfide. So again, it's really, even though it really is a nonmetal, because it sort of behaves like an acid in a lot of cases, it's sort of treated more ionic. So it does sort of follow kind of like type 1 naming. You just call it hydrogen and whatever the other part of it is. But it will not definitely use any prefixes or anything like that for anything that involves hydrogen. All right. So let's try some here. So for each of these, give the proper name. And let's do some names, the formulas. So let's do dinitrogen. Pentasulfide. Let's do carbon tetrabromide. And let's just make up one. Let's do trioxygen. Hexoxide there. All right, so names on the left there and formulas on the right. Look at these, and again, these really should be probably the fastest ones that you do because there's nothing to balance. There's nothing really to think about other than get the right prefix. When we look at this, we have I, which is a nonmetal, and O, which is a nonmetal. So that automatically takes us to type 3 and prefixes. So a prefix for 2 is di, and we use the whole name of the first element. So that'll be diiodine. Prefix here for 7 is hepta, and that guy does get the IDE at the end. And we will drop the A off of the hepta there so we don't get the A and the O backing up to each other. And we get our diiodine heptoxide there. Any questions on that one there? And again, here the two I's are okay in this case. The C, which is a nonmetal, the O, which is a nonmetal, again tells us it's type 3. We have one carbon prefix for 1 is mono, but we do not use it on the first name. So we'll just use the entire first name here of the element, which would be carbon. The prefix there for 2 is di. And again, we give the oxygen the IDE treatment there at the end. It says carbon dioxide. Looking at the last one, that is phosphorus, which is a nonmetal, chlorine, which is a nonmetal. Once again, we have just one of the P's, so that is mono. We will not use it on the first name, so that is phosphorus. And prefix for 3 is tri, and a chlorine becomes chloride at the end. Any question on any of those names? Yeah, probably the fastest and easiest one of everything that you ever name is what we have on the right, which is the naming, going from the name back to the formula. As soon as I look at this formula, I see prefixes. I know it's type 3, which means I'm just going to basically write what is there. Di is 2, nitrogen is N, so that's N2. Penta is 5, sulfur is S, so there we go, N2S5. Nothing to balance, just need to write what's there. Carbon, no prefix, but I do see a prefix here. Tells me it still is a type 3 compound. No prefix means mono, which means there's one of them. So I'm just going to write C. Tetra is 4 and bromide is Br. And that is it on that. Yeah. Lastly here, tri and hexa basically. So tri is 3, oxygen is O. Hexa is 6, and did I do oxygen twice? I did. That is definitely a made up one right there. I can see all my examples like oxygen on the brain already. I did like 90 of them already with oxygen, but so 0306, the classic 0306, which is clearly what you're looking for. So maybe a different element would have been better there on the second one, but we'll go with it here. Any questions on these terrible example there at the end? All right. So type 3, again, two nonmetals. This is where prefixes happen. And again, there's no mixture of any of those things. So as we talked about before, you shouldn't be doing any type of Roman numeraling and prefixing together, because it's one small place where that might happen. But you never should have really a Roman numeral and prefix. So type 1, no Roman numeral, no prefix, because it is a fixed metal, right? Type 2, no prefix, but you do need a Roman numeral because it has multiple charges. Type 3, prefixes, no Roman numerals because they're nonmetals. Any questions on any of those different things? All right, let me try to do some more oxygen examples here. All right, so there's just a review of what we just talked about. Type 1, nothing. Type 2, Roman numerals, and type 3, prefixes. So let's talk a little bit about polyatomic ions. So polyatomic ions are actually groups of nonmetals that are bound together. So they're kind of interesting things. They are actually held together through covalent bonding, sharing of electrons, but overall they have the actual charge. So they're basically ions, and they're basically treated like an ion compound. So when we look at something like this here, which is NH4, NO3, there's actually two polyatomic ions here. This guy over here is NH4 plus. The one nitrogen and the four hydrogens are all together in one unit, and they're sharing electrons. Actually, they're covalently bonded together. They move around as one unit, and it has a +1 charge. We actually drew it, I think, when we did Lewis structures. It looks something like this. This guy over here is another polyatomic ion, which is NO3 minus. That one nitrogen and three oxygens are also sharing electrons together, but overall has a charge, so it is an ion. And we also drew that guy too, if you remember. It looks something like this. So they are both really still ions, which means we come back to our normal, put a positive and negative guy together, we basically need to get to 0. So that is why when we take this guy, which is basically +1, and take this guy, which is basically -1, and put it together, we just need one of each of them, which gets us to our formula here of NOH4, NO3. Each of these polyatomic ions actually has a specific name. So for example, the guy on the left there is what is known as the ammonium ion, not to be confused with ammonia, which is NH3 no charge. NH3 no charge is ammonia. NH4 plus is the ammonium ion. This guy over here on the right is the nitrate ion. The good news about polyatomic ions is, frankly, you just use the name. Doesn't matter how many you have of them. You just use whatever their name is. So in this case, we would put it together, and this guy would be ammonium nitrate. And it doesn't matter with polyatomic ions if you got like 3 of them, if you got 2 of them, you got 1 of them, you just use the name. So again, no prefixing or anything with those guys, just the whole name of it. Now, in most cases, most polyatomic ions are negatively charged. So pretty much most of them are negatively charged. There's a few that are positively charged, like NH4 plus or hydronium, which is H3O plus. But for the vast majority of polyatomic ions, what you're going to end up having is a metal and a polyatomic ion coming together. So the metal will be your positive guy, your cation. The polyatomic ion will be your negative anion. And what that basically means is, as we talked about previously, whenever there is a metal involved, it is always the most important thing. So in most cases, you'll have a metal and you'll have a polyatomic ion together, which means you basically default back to type 1 or type 2 sort of naming. And what that means is, just like in type 1 or type 2, if the metal needs a Roman numeral, you need to put it. And if the metal doesn't need a Roman numeral, you don't put it. So you basically fall back to kind of type 1 and type 2 naming when we're dealing with polyatomic ions, because most of them are pretty much negatively charged. Any questions on that there? So if we look at a table similar to one you got in your book of some of these polyatomic ions, and you do have to sort of know them and the formulas and the names. So you do need to know the names and the formulas, including their charges, so you can put everything together properly. But there is a couple of ways that you could kind of group things together to help you learn them. So for example, if you take something like NO3 minus, that is nitrate. Take something like NO2 minus, that is nitrite. Take something like SO4 2 minus, that is sulfate, ATE, and SO3 2 minus is sulfite. When you have typically a group of two that are related to each other, and the one with the most oxygen in that group of two will end in 8, and the other guy will end in ite. So typically the one that ends in 8 has the most oxygen. Everything else is exactly the same. The charge is exactly the same. The main element other than oxygen is the same. The only difference is the number of oxygens that you have. And the one with the least amount of oxygens is ite in a group of 2. And again, this guy has a -1 charge, so does this guy. This has a nitrogen, this has a nitrogen. The only difference is the number of oxygens. Same thing here. This sulfate has a -2, this has a -2, has a sulfur. Sulfur difference is the number of oxygens. So sometimes people will learn perhaps all the 8s and know that the ites are just 1 oxygen less. Everything else is the exact same. Or you could learn all the ites and know that the 8s are basically just 1 oxygen more. So that's a good way to kind of learn them. If you don't want to kind of learn them individually, just learn all the 8s that are there. And if you need to adjust down an oxygen, they all become ites and they have 1 less oxygen. And that's a good way to sort of learn it. Other things that we see is sometimes there are groups of 4 that are related, like these guys right here. That's a very common group of 4. That is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. They all have a -1 charge. They all have chlorine. The only difference is how many oxygens each one has. The guy on the left there has 4, 3, 2, and then 1 oxygens. They're actually named very similar with the 8 and the ite. In a group of 4, you could kind of break it apart into groups of 2. And the 2 that have the least number of oxygens should end in ite, like we were just talking about. So this guy here would be chlorite. This guy here would also be chlorite. Obviously, you can't have the same name for 2 different things. So in a group of 4, the one that has the least number of oxygens will end in ite and also start with hypo. So it'll start with hypo and end in ite. So this guy is actually hypochlorite. Chlorite. You could kind of follow the same logic for our 2 on the left there that has the most oxygen. Those each will end in 8. So this guy would be chlorate. This guy would also be chlorate. Again, you can't obviously have the same name for 2 different things. So in a group of 4, the one with the most oxygen will also start with per. So this is what is known as perchlorate. So perchlorate, chlorate, chlorite, and hypochlorite. Those are a very common group of 4 that are related to each other. And again, only in sort of a group of 4, you get the per on the guy that has the most, hypo for the guy that has the least number of all of them. These also work the same way. If you look at group 7, that is where we find chlorine. You could swap out chlorine in any of these here, and it'll be named very similar. So for example, if you took BrO3 minus, instead of chlorate, we took out the chlorine, and this would be bromate. So it works the same way. If I had BrO2 minus, it would be bromite, ITE, just like it was chlorite. So it works the same way. If you threw a iodide in there in this place, IO3 minus would be iodate and iodite. So you could swap out the halogen in that group of 4 with any of the halogens. They're basically just named the same way. Just take the chlorine part out and kind of substitute in the other element's name, and you'll have basically the same name. Other things that you commonly will also see on these polyatomic ion tables is sometimes we will put a hydrogen or H+ ion in there. So this is carbonate. And if we take carbonate basically and put an H+ in front of it, we get a hydrogen HCO3 minus, because this is -2, that is +1, that leaves you a -1 overall charge. This is what we just did, is basically put a hydrogen in front of it. This is what is known as hydrogen carbonate. Now, of course, it's chemistry, so they must confuse it a little bit more. In addition, historically, they didn't use hydrogen, but they used the word bi instead. So this is very commonly referred to as bicarbonate. So bicarbonate and hydrogen carbonate are exactly the same thing. It also happens with sulfate. If you put a hydrogen in front of sulfate, it is known as hydrogen sulfate and also known as bisulfate. So if you see the word bi in front of something, it usually will mean, in this case of a polyatomic ion, that it's hydrogen in front of whatever the part is. Take the bi out and just put hydrogen in front of it, and it's the same thing. So there are some polyatomic ions, though, that do end in IDE, like hydroxide, cyanide, azide. So there are a number of ones that do end in IDE, but most of them will end in ate or ite. And again, you really will use sort of the metal type 1 or type 2 with it as you go through it. Any questions on that there? I mentioned earlier that there's like one place where perhaps you would have a Roman numeral and you would have sort of a prefix, and this would be the place where it could happen. And it's not because you would put the prefix on, it's because the prefix is part of the polyatomic ion name, like dichromate, right? That's just the name of it. So if you had that, it's possible you could have a Roman numeral and dichromate. There's not a di that you put on there, it's just part of the name of the polyatomic ion. So that would be the only one exception where you would have like a Roman numeral and a prefix happening, because the prefix is part of the actual polyatomic ion's name as well. So here's permanganate, right? And permanganate, although it doesn't look like it, it also is like a group of 4. That's permanganate, like perchlorate. And you could have MnO3 minus, which would be manganate. Instead of permanganate, it would just be manganate. You would have MnO2 minus, which would be manganite, and MnO minus, which would be hypomanganite. So sometimes these guys can kind of expand out, and they follow sort of the same pattern. Any questions on that there? Yeah. It has to do with really the charge that we see there has to really do with kind of like the bonding that we talked about, and it has to do with what's referred to sometimes as the formal charge. So again, depending on the numbers of ions, the number of atoms that are there, and the bonding that's going to happen, each of those sort of elements in that arrangement will take on some different oxidation states, for example, charges, and that's what sort of keeps the overall charge still the same. So for example, if you look at ClO4 minus, for example, and you look at ClO3 minus, and your question is, how could it still be -1 overall? What happens in this case, and this is obviously outside of our class, but what we would look at is what's referred to as the oxidation state, which is kind of the charge that that element has while sharing electrons with everybody in this sort of arrangement. So in this case, the oxygen would have a -2, which means there's 4 of them, which would give you a -8. And overall, this has a -1 charge, which means the chlorine in this particular case actually is taking on like a +7 charge. As opposed to if we go to the guy below it, the oxygen will still take on a -2 sort of oxidation state, and it will end up with a -6 overall equals -1. So in this particular case, the chlorine actually drops down to only like a +5 sort of arrangement in terms of its charge. And it has to do with really the sharing of electrons, electronegativity, everybody that's there, as to how that element sort of takes on different ones known as oxidation states. So that's how the same thing that has like sort of the same charge overall is really because the central atom is actually taken on a different oxidation state. That's how it ends up being the same overall charge. Other questions? All the way down to like the ClO minus, where the chlorine is actually just like a +1 sort of charge in that situation. Has less oxygens there, so it's not taking on as much of a positive charge. As the case with the 4 oxygens, it's more electronegative than carbon, so they're sucking out a lot more of those electrons from the chlorine, making it more electron deficient and more positive. So that's how it gets a higher sort of positive charge. Other questions on that? All right, so why don't we try some here? We'll leave the chart up here. Let's try some names, and then we'll try some formulas. So let's do CaNO32. What's the name of that guy? Let's do a little FeSO4. Let's do Cu3PO4. And let's do some formulas for, let's do sodium bicarbonate. Let's do copper to chlorite. And let's do ammonium sulfide. All right, so names on the left there, formulas on the right. So let's take a look, see how we're doing. So once again, I see a metal and I see a polyatomic ion. So whenever the metal's involved, as we've been talking about, it is the most important. And that is calcium, which is group 2, which means it has a fixed charge. So it's a type 1, which means, frankly, all we need to do is roll right into the name, which would be calcium. And remember, the polyatomic ion, we just use the name of it. It doesn't matter how many there are of it. So this would be calcium nitrate. The 2 again here has no effect on the name. And again, no prefix or anything like that. Now, when we do look at this polyatomic ion, there is parentheses there, which is important. Because if I didn't have the parentheses and wrote it like this means what? I got 32 oxygens, which is not really what I want in this case. We do need to put always, when there's more than one polyatomic ion, you need to put the parentheses around it and the number on the bottom, because really what we have here are some ions. We have a calcium ion that's a cation, and we have 2 of these nitrate ions floating around. And again, that is what the 2 represents. So whenever you have more than one polyatomic ion, you got to parentheses it up and put the number on the bottom to help you do that. Any questions on that one there? Looking at this is iron, which is a metal, sulfate, which is a polyatomic ion. Once again, this metal here tells me it is type 2. So once again, I'm not maybe sure what it is. If I look over here at sulfate, I will see it's SO4 2-. That means that my iron here needs to be +2 to balance it out. And this would be iron Roman numeral 2 for the charge. And once again, here we'll just use the whole name there of the polyatomic ion, which would be sulfate in this case. Yeah. Any questions on that one there? Coming here to our last one. Once again, we got copper as a transition metal, and copper again is type 2. Our phosphate is right here, which is PO4 3-. That means in this case, each again for the charge there. Any question on any of those names? Coming to the right there, we're going to put it together. So sodium is Na+, bicarbonate is this guy right here, which is hydrogen carbonate. And in this particular case, we are basically putting -1 and +1 together, which means we just need one of each. So we'd just put it all together, HCO3. No need for parentheses if there's just one. You don't need to put the parentheses around it. Coming here, copper Roman numeral 2 tells me my copper has a +2 charge. That is what the Roman numeral says. Chlorite is right there. That would be ClO2 minus. In this case, that's -1 and +2, which means we do need two of these guys to balance it out. That means our formula would be Cu. We do need now parentheses, ClO2, and the 2 on the bottom there. Question on that one there. Lastly here, ammonium, which is a polyatomic ion, which is NH4 plus. And sulfide is actually from the periodic table. That's group 6. And that is -2. That means in this case, we actually need 2 of the ammonium ions to balance it out. That is 2 polyatomic ions, which means we will put that in brackets there with a 2 and an S at the end. Any questions on polyatomic ions, how to put them together, name them? Basically, for the most part, it's going to be a type 1, type 2 situation, and probably 99% of the time. So just fall back to those same rules. And again, regardless of how many polyatomic ions of it. Any questions on polyatomic ions? Okay, last thing we're going to talk about in terms of naming is, I'm just going to roll it right here, is acids. And acids are substances that can produce H+ ions in solution. That is basically what makes something an acid, is the ability to do that. And what I mean by that is actually free H+ floating around in the solution. That's what pretty much makes something an acid. H+ and H3O+, which is the hydronium ion, also a polyatomic ion, is basically equivalent to each other in acid-base chemistry. So if you see H3O+ or you see H+, it's basically the same thing. It means the acid part of the solution. It could also obviously be represented by H3O+ floating around in the solution. So the ability for something to release the H+ into the solution or H3O+ into the solution is what makes it an acid, and the ability of it to do it really well and easy makes it a strong acid versus something that doesn't do it so well. It's a weak acid. When we come to naming acids, and because they are in solution, we always include usually the aqueous symbol next to it. And that aqueous symbol means that it basically is in a solution that the ions are floating around. So when you have something like hydrochloric acid here, you typically do put the little aqueous symbol next to it to let you know that it's hydrochloric acid here rather than HCl that's maybe a gas, which would be hydrogen chloride versus hydrochloric acid. So usually you include that next to your formulas when you write the formulas for acids so that everybody is clear that it is the acid. How we go about naming acids is not too bad. It all revolves around pretty much one element, and that element is oxygen. Whether or not the acid has oxygen or does not have oxygen. If the acid has oxygen, it's what is referred to as an oxyacid sometimes, because it obviously has oxygen, and obviously if it doesn't, it will not. So if your acid, the answer to oxygen question is no. The way that we name those acid is it starts with hydro, something ic acid. So for example, the HCl that I just did there. By the way, what makes something an acid is the ability to give away the H+. So for all acids, the cation or the positive ion is always H+. So that is always the positive guy when you're writing a formula for an acid. So really this acid here is H+ and Cl-. It's ionic, so one of each, put them together gives us HCl, which is the proper formula for it. No acid, no oxygen here. So this would be hydro. The missing part is the negative guy, which is chloride, right? So this would be hydrochloric acid. HBr would be hydrochromic acid. So if your acid does not have oxygen, it will always start with hydro. It will end with ic. It will be acid at the end middle. The part is the negative guy. So whatever that negative guy is what you would fill in there. Now, if your acid does have oxygen in it, so if your acid has oxygen and the answer is yes, then it will contain what we just were talking about, our favorite things, which are polyatomic ions. And it will contain a polyatomic ion, which we just talked about, will end in one of two ways. Either they will pretty much end in 8 or they will end in ite, right? Those are pretty much the two ways that they do it. So if your acid does have oxygen and your polyatomic ion ends in 8, your acid is something ic acid. Like you ate too much is icky. There is no hydro, by the way. Here, hydro is for things with no oxygen. So if you take something like HNO3, NO3 is NO3 minus, which is nitrate. This becomes nitric acid. The cation is H plus, the anion is nitrate. If I take H2SO4, SO4 is SO4 2 minus, which is sulfate. This would be sulfuric acid. The cation here is H plus. That's why there's 2 of them to balance out the charge on the sulfate. You need 2 positive pluses there, right, to balance out the -2 on the sulfate. Again, no charge when you put it together. If your polyatomic ion ends in ite, your acid will be something OUS acid. So if you take HNO2, NO2 is NO2 minus, which is nitrite. That means that this would be nitrous acid. Again, the cation here would be H plus in this case. You had something like H2SO3. SO3 is SO3 2 minus, which is sulfite. This will be sulfurous acid. So if it ends in ITE, OUS for the acid. And if it ends in ATE, the polyatomic ion, IC. If it has oxygen and it's an acid, you should never have hydro. Yeah, it's wrong. So hydro is only for the ones with no oxygen. That's an acid. Question on that there. Just look at 2 here before we get out of here. Just to show you how to go backwards. Say you had carbonic acid, and say you had hydroiodic acid, and let's just say we had chlorous acid. So if you have the name and you want to go backwards, a couple things that you want to look at is this. When I look at this acid name, I do not see hydro, which tells me it has oxygen. And because it has oxygen, it has a polyatomic ion, which means I could go to here, and that's ic. And ic goes with polyatomic ions that end in 8. So that's like carbonate, right? And that tells me that is the polyatomic ion that I am dealing with, carbonate. And I know always the acid H plus is the positive guy. So when I put this together, I need 2 of these guys to balance it out to get me to my proper formula here of carbonic acid, which looks like this. When I look at the guy over here, this is hydro, which tells me it's an acid that does not have oxygen. So that's pretty much H plus, and iodine is I minus. So that would be HI when I put it back together. And lastly here, I see this with no hydro, which means it has oxygen. It's a polyatomic ion. And if I get rid of OUS, I know that is for ite, which means that's like chlorite. So I know it is chlorite is my actual polyatomic ion. And I know once again, my acid will have H plus, so I could put them back together here. In this case, HCO2 as my acid. So if you have the name of the acid, you can kind of deconstruct it backwards. And if it does contain oxygen, get rid of the ick and put the 8, and it'll kind of tell you the name of the polyatomic ion. And if it is OUS, get rid of the OUS and put ITE, and it'll again tell you the name of the polyatomic ion. Question on how to name acids or anything else? All right, I think we got all of our naming in for today.